Hi everyone, today we're going to be talking about Physics 252, Week 7, problem number 1. In this problem, we are asked to take a look at some standing waves inside of a hallway that is in open-closed orientation. And this is going to be important throughout our problem, and you'll soon see why. So, what we have given in this problem is we're given the length of the hallway, as well as again, our open-closed orientation, and the velocity of air. So from lecture this week, we learned a lot about kind of standing waves, and actually in chapter 17 of the book, more specifically the chapter on superposition, we kind of go over the different types of tube orientations and how sounds kind of resonate, or their standing waves move when they're inside of the tube here. So just getting into the problem, so I've gone ahead and written down some things that I found helpful. The first of which being this equation here, which is given in the book for the wavelength at a given mode. And so the mode of the standing wave is essentially the harmonic of that wave. So for our open and closed orientation tubes, we have to remember that our modes increase only on odd integers. So this is a topic that's discussed in the book, but I've kind of tried to draw a little image here to help actualize this. So we can think of this as our hallway here. This may be one side, and this is our open end. And this would be our first mode here, with one node right here. This would be our fifth mode right here. This would be our third mode, and so on. But one thing that's important to note about this equation is that when you have a really long length, you have a really long wavelength. And when you have a really long wavelength, you end up having a really small frequency. So that's something that we'll see throughout this problem. So moving along, here's just this equation rewritten, and we'll be using this as kind of our way to find the higher order harmonics of this tube. This right here is the threshold of, or I guess the value range in frequency of human hearing. So this is what we're capable of hearing. So just getting started here, for A we have our lowest harmonic. As you can see, we're just plugging right into this equation here and solving for F1, or the first harmonic, which we find out to be 6 hertz. Then for the third harmonic, we just multiply using our odd numbered mode, and multiplying it by F1. We get 18 hertz, and just kind of so on. You know, we can keep doing this. One thing that we can notice is that we'll only really be able to hear this sound at the fifth harmonic, and we'll be able to hear the sound up until the 3,337th harmonic, which I found to be pretty interesting. That just seems pretty high, but that is the highest. So at this point, it will be just out of our range of human hearing. So if we were down one more harmonic, what would it be? Just 3,335 would be the maximum that we could hear, but this is just out of our range here. What we can do here, we can go ahead and say for part C, we want to figure out what the ghost frequency is. And this is actually a really cool thing. I don't know if you have heard this before, but at 18 hertz, since it's so close to being within our range of hearing, that it makes a very ominous hum, and it's supposed that when things feel haunted, especially machinery, it kind of can emit this frequency of vibration, and it's just very off-putting. I mean, it sounds like any horror movie that you've seen. So I'll go ahead and link that in the description for this video so you can take a look. But I thought that was a pretty cool thing. And one thing I just noticed, this greater than, this is wrong. This should be the fifth right here. So my bad. But I hope you found this video helpful, and thank you very much for watching.